Welcome, everyone, to the opening roundtable for the 2026 Brown Center for the Fundamental Physics of the Universe. We usually abbreviate it as CFPU, AI Winter School. This is the third annual Winter School for the CFPU. I'm Dell'Antonio. I'm an astronomer here at Brown and Associate Director of the CFPU. And it's my pleasure to introduce our roundtable panelists. So let me introduce first Phiala Shanahan. Phiala is an associate professor of physics at MIT, interim deputy director of the NSF Institute for Artificial Intelligence and Fundamental Interactions, which I'm not going to try to pronounce as IIFE. Also headquartered at MIT. She's a particle physicist working on understanding the gluon structure within between protons and neutrons. Second is Brenda Rubenstein. Brenda is a professor of chemistry and physics at Brown, and she's the director of the Data Science Institute at Brown. Her research is focused on the use of AI in quantum mechanics and biophysics. Third is Jamie Macbeth. Jamie is associate professor in the Department of Computer Science at Smith College and also a graduate of the Brown Department of Physics. His research builds cognitive artificial intelligence systems to explore the content of non-linguistics and iconic mental imagery representations and the intersections with understandings in robotics and planning. We will hopefully shortly be joined by Michael Littman, who's an AI researcher at Brown and is the associate provost for AI at Brown and was also division director of the National Science Foundation, helping to coordinate the AI efforts across the agencies. I want to welcome you to this opening discussion. The idea of this opening discussion is to introduce topics in machine learning and artificial intelligence and give students and attendees a sense of the path forward or potential path forward. So to get the discussion started, I wanted to ask each of you to weigh in on the rapidly increasing role of AI and machine learning in physics research. And as you look at the current landscape in machine learning, what machine learning technique is still underutilized in your opinion? Or if you prefer, if you think there's something that's overutilized, which technique has become overutilized? So I'll start, Phiala, do you want to start?
Sure, thank you. So from my perspective as a theoretical physicist, I'm not going to answer in terms of machine learning technique, but a perspective. And I think a perspective that's underutilized still is to consider how the problems are framed as to where machine learning can be inserted into a solution pipeline in such a way that you can still guarantee exactness and mathematical rigor. So maybe machine learning is not used to solve a problem. Maybe it's used to transform a problem into a different form that can be solved more efficiently by standard algorithms with standard exactness guarantees. So an example of that is a change of variables or changing a complex contour. If you deform the contour, as long as you don't cross a pole, you have the same answer. And if you're trying to do a numerical integration, maybe you can transform it to a much more efficient contour. Maybe you want to do sampling and you can sample efficiently from a nearby distribution, but you can reweight, so you still maintain exactness guarantees. Maybe you want to invert a matrix, and instead of trying to invert the matrix with machine learning, you learn a preconditioner, and then you invert it using standard algorithms. So the perspective that I think is underutilized is that you can have rigorous mathematical guarantees of exactness in solving your physics problems. You don't necessarily need data. You can use equations to train your machine learning approaches. And it's just a question of where and how machine learning gets inserted into a problem pipeline. It's not necessarily I need a lot of data and there'll certainly be uncertainties in a black box. It's a very flexible tool, and perspective is different perspectives are possible on how you implement it for solving physics problems.
Excellent. Maybe I'll segue to Jamie. Do you want to address maybe a similar question or how AI can be used to address different sorts of problems?
Sure. Yeah. I mean, I'm gonna take the which technique has become overused part of the question, and I'm really glad that you're asking this question because I think, and I'll my view is more from the field of artificial intelligence as a whole. I think that the field has become over the past couple of decades way more has gotten a way more narrow focused on focusing on particular methods that are deemed to be successful according to what's happening on the leaderboards in terms of solving certain kinds of problems, and people, we become narrow in terms of the methods that we allow each other to study. And people say, well, that method there is the old method. You shouldn't try that again. You should try the methods that are performing well. And I think that's I think the problem with that is that I think everybody winds up scooping each other, doing the same thing, and lots of resources going to a single idea or a few ideas. And I think we should fund and explore and investigate a broader variety of techniques beyond just you could say if you're one of the main foci now is deep learning, large language models, and so on. We can allow ourselves to explore things that are just interesting. We can allow ourselves to revive old methods that are interesting and maybe lost threads. There might be even interesting things to do when we're building systems by hand without machine learning that might be relevant to machine learning problems later. And so I think it's that's my perspective on it. And I think it's great that people are using machine learning and AI to study physics and not just try to make $1 billion off of self-driving cars or something like that. I think that the fact that we're here discussing AI and physics is an important part of broadening the focus of these kinds of research. But I think also we should be broadening the focus of the kinds of AI and machine learning techniques that we allow ourselves to use and to study.
I'm going to come back to you in a second for a follow-up on that. But Brenda, do you want to tell us a little bit about your perspective on this?
Sure. First of all, welcome everyone to the AI Winter School. It's great that you're keeping yourselves warm with our very in-depth thoughts and inspiration. So I come from the field of condensed matter for the most part. So I sit at the boundary of chemical physics and condensed matter physics. For us, techniques that have been widely used and are incredibly successful are things like machine learning potentials. So these are potentials that basically very rapidly learn what is the solution to the Schrödinger equation across a wide variety of different configurations or different phases and so forth. These techniques are wonderful, and we have many techniques that are out there. But I think the thing that I would press for is thinking about how we actually think and interpret data from the perspective of physicists. And I'd like to press for, and I guess I would argue for, thinking more about how does AI actually interact with our philosophy of physics and how we as humans think about physics. So moving forward, I am, at least personally, I am persuaded that we'll have great ML that's going to be able to uncover data, interpret data, and maybe find some trends that we don't have. But the bigger question for me is just we've built up physics such that we have an understanding of what knowledge is. We say that knowledge is maybe we understand an equation, and that equation now we can apply that equation to this scenario and that scenario and some other scenario, and that's called knowledge. What machine learning is doing and AI is doing is perhaps changing that perspective of knowledge. So instead of, let's say, having an equation or some very persuasive idea that's knowledge, now it's going to be, some, let's say, neural network, could be some other architecture, but a neural network that is going to give us some information. And I think what we have to start thinking about is how do we actually view that information? It doesn't fit in our typical maybe physics boxes of I now understand this concept. And also, as these machines become more powerful and perhaps unlock new things, how are they going to feed that information in an understandable way to us such that we appreciate it? And so I think moving forward, we have to start thinking about that human AI interaction a lot more than at least I've personally seen in the past.
Thank you all. I very much like the synthesis of all three of these opinions or these three viewpoints, because they really highlight the idea that there is a knowledge in physics or a knowledge base in science, and using that knowledge base alongside AI and machine learning is an important problem. Because it is very easy to get an answer out of an algorithm. I assume almost everyone in the audience has typed something into ChatGPT and gotten an answer. But we also know lots of things about physics that aren't sort of in the published papers or in their ways of thinking, and incorporating those ways of thinking, I think that brings up, as a link to some of the things that Phiala was mentioning. Um, Jamie, you'd mentioned other techniques. Do you want to elaborate for a minute on other things that could be done that are not, say, large language models? Maybe I'm going to try to push you on the underutilized aspect. What's underutilized at the moment?
Yeah, I mean, I think part of the answer that I should have given is that I'm not pushing any particular technique I could push my own perspectives, which are these. I guess maybe that's the convenient thing to do here. So thinking about large language models, I think the important thing to remember is that they are trained on huge, vast bodies of text, so big that no particular person, any of us, could ever consume it all in a lifetime, even if we did nothing but read and never slept. But they don't appear, in many ways, they don't appear to have the same, let's call them models of the world, or as often what I often call in my research is non-linguistic imagery models and systems that I think humans need for understanding things, and particularly for understanding the physical world. And we don't understand enough really about how those work within people. They don't seem to be able to make themselves into large language models just by processing lots and lots of text. So I think that's an important barrier to consider when we're looking at large language models as tools to use to help us with physics. But I think also, let me say this, I think if we better understood the kinds of representations that people use kind of generally, but also that the kinds of mind representations that physicists use, that we could possibly build those into our AI and machine learning systems and have better companions and better collaborators when we're working on physics. But there's a lot of evidence out there that large language models don't really have the world models that they need to understand things the way that we understand them. And they're, in surveys recently with the Association for the Advancement of Artificial Intelligence, the presidential panel surveys last year, a large majority of people don't think that they're the route to what you might call artificial general intelligence or human level intelligence. So there still needs to be a human in the loop. And I think other people have mentioned, you also mentioned that idea that the human needs to be in the loop.
Phiala, I think I wanted to bring this back to the theoretical physics aspect. When I talk to my students about how I view physics, it's largely a question of context. The equations don't live by themselves. Our understanding of the world comes from that context. And I think one of the things Jamie mentioned is that's the context. How do you get that context into a machine learning environment, so that you're not just tokenizing information so that it can be sorted very rapidly is great and can find interesting patterns, but you don't want to lose the context of how the physical world works in the way that we've built it up in the last 100 years.
Yes, I'd say that's part of it. How do you get the physics into the machine learning, but also the reverse? Where do you put the machine learning into the physics so that you're not trying to do that, right? Can you find a place where a machine learning algorithm can do something different for you than just try to solve the problem rather than trying to restrict it to solve the problem fit it into the box of the physics we're trying to do? Can I find a different place in my problem to put machine learning where it doesn't matter, where I have ways of correcting, where I don't need to have a data set, I don't need to have an understanding of that data set that then informs my understanding of the model that I have to understand in order to understand the physics, right?
I want to move now possibly to the second question, which is a more forward-looking question, which is one of barriers. I mean, some of these barriers we've brought up already, but what barriers do you see to the applicability of machine learning in physics or in other sciences, if you prefer, right? Because this is not a purely physics problem, even though we're sponsoring it by physicists. So I'm going to start. Jamie, do you want to start uh, addressing this issue of barriers to applicability? You raised this issue of the sort of worldview. What other barriers does AI have to being more useful in physics, let's say?
Um, I think barriers other than worldviews. Uh, I think that's a real clear one. Um, you know, I so as I was saying, I think the way to view large language models, or one view that's out there for and maybe my response is a little bit more focused on large language models and on other kinds of ways that people are using machine learning in physics research, but um, you can view it as something that predicts the most likely next word or next content based on what's come before it in the prompt, based on a huge corpus of natural language. And I think one of the problems that's with that is you'll often find, or you maybe not very often, but enough such that it's a problem, you may often find that the answer to your question, or the answer to your query or to your prompt, is something that is very unlikely. It's a very unlikely answer to your prompt. We have the world models for reasoning about things such that we can come up with an answer that was not probabilistically most likely based on the corpus of language, or also you could say in other areas maybe based on a corpus of mathematical texts or physical texts or other scientific texts. Um, uh, but the correct answer is something that's less likely, and so I think that's another barrier to using these kinds of systems that are highly focused on giving you the content or giving you the answer that is probabilistically very most likely. You'll end up with something that's very average and flat, possibly when you really needed something that was rare and unusual and had kind of a long tail to it.
That's interesting because I think when I was first exposed to the idea of machine learning now many years ago in within physics, it was in the context of large data sets and rare events, where the whole point was finding the uncommon in a large data set. And in fact, there is still a large anomaly detection aspect to machine learning. Um, Brenda, maybe the same question to you.
Sure. So I 100% agree with I think the themes that we've been talking about of humans interacting with the AI. Let me name one other facet of that, which is also perhaps an obvious facet, but sometimes people don't think along these lines. I'll talk about data. So many of the models that are out there that are very popular are trained on very common data. But if you look towards other fields and different areas of physics, but also if you move more towards chemistry and biology, there's a lot of desire for AI to solve problems that we really haven't before. But the problem with that is that also requires that we start developing data in perhaps areas that we haven't before. So Phiala was sort of saying this, a lot of us want to use AI to basically solve problems that we actually already know the answer to. We feel comfortable, we can check it, we can do some things with it. But if you actually want to use AI to discover new things, to understand new things, we also need data from those different situations. So I'll give you an example from chemistry. So for decades, people have been thinking about how do we develop new pharmaceuticals, and there's actually a point where many people would say that we're kind of at the end of the line there. People actually have been saying that for maybe 20, 30 years, that we can't do any new chemistry anymore. We've kind of saturated what's called organic chemistry using CH and O's and so forth. If we want to go beyond, we would have to understand how different crazy metals work. We have some understanding, but we don't have a lot. And so a lot of people are saying, well, ML is just, they're actually huge companies that were founded on this. They're actually on the stock market at this point. We're saying ML is now going to tell us how we're going to make new molecules from these crazy metals. But the problem is that we don't have data there because people don't know, they weren't able to actually do those reactions themselves. And sometimes they never even thought in those different directions. And so data has to be there in order to make those discoveries. And I link that to humans again because of the fact that, we are trained to think in a certain way. We have our own models. These models may be very biased in our minds because of the way people did things in the past or the way we ourselves have done things in the past. And so if we want AI to actually branch out, we also have to be able to branch out to those new spaces where new data can be generated.
Welcome, Michael Littman. I apologize. I introduced you in absentia, but I wanted to bring a question to you about this was a question about barriers in AI and machine learning applicability, and link it perhaps to the current state of AI and what needs to be done. So Brenda pointed out that in fact a lot of the things require a lot of the techniques require knowledge of uh, some background to know whether things are the return from the machine learning algorithms are at all useful or correct. Are there other barriers that you can see to the usability of machine learning? And
Yeah, thanks so much for introducing me in absentia. I'm so sorry. It was very clearly marked on my calendar for 3 p.m. today, not one whatever this actually turned out to be. I don't know if that was a time zone issue or if I just logged it incorrectly. But anyway,
no
I'm so sorry. I hope everybody's doing fine. So yeah, so I think that's Brenda makes a great point. I think there's tons of issues, I think, but the one that I would want to highlight is something around the idea that the way that the machine learning systems are designed and developed and what their mathematical underpinning is, it's very much learning a function with respect to some fixed probability distribution over inputs. And I think that science, and I'm not a physicist, I'm a computer scientist, so you know that I'm not a scientist at all because it says it right there in my name. My sense is that scientific theories have a certain kind of generality or context independence that's really important. That these laws should hold independent of the probability distribution over which you're sampling data. And to the extent that we're applying these machine learning methods to data that we've collected, that those distributions are getting baked in ways sometimes that are very difficult to separate out. So I think there's work that we can do on the machine learning side to make these systems more independent, more context independent. I mean, like what we do now, if we want a system to be general, right, to actually generalize beyond the data that it's trained on, what we do is we get a lot more data, right? We just keep hitting it with data and data and data with the hope that the system will actually become more general. And typically what it will do at that point is incorporate more and more of the context into its prediction, right? So instead of boiling it down to find like the gem of the physical law, the thing that's actually predictive, it's just using whatever kind of context cues that it can develop to make those predictions. And that actually turns out to be really powerful and useful in a practical setting. I think things like doing weather prediction, what we're finding is that actually turns out to be a reasonable thing to do. So you can do it. You can make the prediction based on purely physical laws, or you can make the prediction based on these machine learning systems that are using much more of the context. And the context ones tend to be more accurate and more efficient and better. But they're going to be wrong when you get to these interesting kind of boundary cases. And that's because they are leaning on the fact that they were trained from a certain distribution. And so to me, that's one of the kind of pain points between what machine learning is really good at and what a physicist might want to do with a system like that. And so that would be my proposal for a topic that I think is in that category.
Phiala, I want to turn to you. Has this conversation resonated with what you're thinking about as a theorist?
Yeah, very much so. So to me, one of the big challenges, and this is from personal experience, I spent the last 3 years trying to implement some machine learning algorithms for theoretical physics on the newest exascale computers in sort of early science time. And one of the challenges is that we want to do things a little differently. Maybe we have different data, maybe we have different structures, maybe we want to use slightly different algorithms. We're not deploying the same out-of-the-box algorithms on the same kind of data that's being used in a lot of the large-scale applications. So in my case, I'm trying to run truly model parallel architectures over thousands of nodes of GPUs. And everything else that was set up has, data parallelism. And, we have to completely re-engineer everything from the ground up because we're trying to do things in a slightly different way for our physics problems. And so I'm a little terrified of the trend towards foundation models. There's a lot to be done there. There's a lot of great there, but there's also a lot of science that we can do by being more specific. And that's one of the things that I'm worried about getting lost around the edges. If we want to do something that's different, this task of having to re-engineer everything because there's a lot of momentum in one direction. And if you say, wait, I need to do something slightly different and at a large scale computationally, and things just not set up, we actually had to go and re-implement complex numbers because they weren't implemented in a way that would work for us, right? I'm talking really, really go back to the ground up because we're using different structures, different algorithms, different data formats.
That maybe brings us back to the point that was raised at the relatively early in the discussion of the way sort of the knowledge of the physicists or the scientists in any other field interacts with the machine learning being complex in the sense that the things that currently AI is good at are not the same as the things that physicists are good at, and finding the right way to make it specific enough. For example, to say, I'm interested in this specific problem. I don't want to throw 3 million existing data sets at the problem because those 3 million data sets might not exist, or because that's not relevant directly to this problem. And so there's this conflict between the things that are, for which there are, the solution is you're looking for a small thing and just throwing all the data set is the way, because no human would ever be able to sift through it all. And computers are very good at that. And I have a specific problem. Is this tool malleable enough to solve this particular problem? Are there other questions or I realized I didn't go around through. I went around through everyone, but I only asked for one specific barrier. Are there other barriers that you can think of that we haven't mentioned to the use of machine learning or to the usability of machine learning in the sciences? I'll open that up to Brenda. I saw a hand.
Sure. This is another aspect of interacting with humans, which again is perhaps an obvious aspect, but I come from the days, I guess I was one of the first young people who started doing computational physics. And I know maybe some other fields started doing computation a little bit earlier. If you're on the accelerators, you're probably using computers a little bit earlier and so forth. But I remember back in that day, everybody sort of said, this isn't physics. And I feel like we're now back at this, where some people are saying this isn't physics. And again, this is a communications issue between what is the AI doing and what are the models that we have in our mind for what physics is. And so I think there's still a barrier in thinking about what is the definition of physics, and also some people who cling to that older definition. So now that I'm in 2026 and I guess I'm a full professor, I sort of laugh when everybody sort of said you could never learn anything with a computer in physics. I think we've learned a lot of things with computers and physics, but that was a very entrenched viewpoint. And in fact, I remember many decades, right before perhaps I was hired, where people would say, I'm doing computational physics, I'll never get a job. Because physics departments didn't believe in it. So there is this mindset that people have, and it still exists out there. And granted, right, we don't know everything about AI. There are lots of issues with AI, and but I think we'll get around those issues. And so we have to start thinking about how do we bring everybody on board, and how do we redefine the constructs that we have in our own minds of our own fields.
And so Phiala and Michael, I saw both your hands up. Before you do, I can share anecdotally that I have had conversations with colleagues that have said, numerical simulations, which are central to understanding cosmology because nonlinear physics you still can't solve. Oh, they won't tell you anything. That has changed, they've changed the field completely in cosmology. Michael, I think I saw your hand first.
And Jan, I should say there's also the why aren't you just smarter? We should be all smarter, but maybe our AIs together with us will be smarter.
I just wanted to flag what did they call it? Uncertainty quantification. So the idea that there's another angle here that I think is really important in the sciences that is not as developed as it needs to be, and I think it's often the scientists who are at the cutting edge of this, is the notion that these models, they make a prediction. Here's my prediction, and it's like, well, is that a good prediction or a bad prediction? It's like, I don't know. It's just trained to make a prediction, and on average, it's making predictions that have low loss. But what we really want to know is this the kind of prediction that, like, this scenario is one where you're very confident that there's reason to believe that this is the actual accurate value, or is this one where, like, let's just take it with a grain of salt? And so incorporating that piece into the way that we use these models, I think, is really, really critical. But yeah, it's interesting hearing you guys talk about the notion that this sort of computational version of it wouldn't count, right? Because I'm on the computational side, and I certainly think that the physics counts. So that is I don't know, that's shocking to me. So thank you for pushing that, in spite of the fact that people may have given you some friction.
My understanding is that the same debate is happening in math as well for many of the same reasons. Phiala,
Yeah, so I want to raise something on the ethics side. And here I'm not talking about the ethics of what if the AI does something crazy. Here I'm talking about the ethics of running extremely large amounts of compute for extremely long times without knowing the outcome. And so that's one thing if you're a private company. But when we're talking about government-funded resources, and so I run, computing resources that cost tens of millions of dollars, and you need some physics output, right? And the question is, do we invest those resources using a known technique where at the start I can give a budget, say I need to do this thing 10,000 times, then my uncertainty will be 0.1%, and I'll have this number? Or do we invest those resources and I say, I'm going to train my machine learning model, and I think it might train this well, but the training dynamics at that scale, of course, you don't really know until you do it. You can make some, and then maybe you get nothing out. And so, what is the right answer for how much of our extremely valuable computing resources we invest in these directions when there is some always inherent uncertainty in trying to do this kind of training at the extremely large scale?
at this valid point, at the same time, I will say that as someone who's involved in a billion-dollar telescope project that might just add another zero onto an uncertainty, I think that's an ethical issue that all large experiments, it's not specifically an AI problem. In general, we're trying to figure out, is this really worth it? And sometimes it is, and it's often unclear whether it will be. I mean, there's always a chance that it won't be. So,
Yeah, I guess for me, the distinction there is that for a number of the applications I'm thinking of, there may be a conventional way to do it. There's a possibility that it's completely unaffordable in the foreseeable future. And so there are genuinely new breakthroughs that you might be able to make using AI, but you can't guarantee them. But maybe if you wait long enough in the future, maybe you could do them with conventional means. So it's not it's not the kind of search where you go in knowing it's blue skies, right? And so I feel it's sort of different from, we have this discovery vision of physics where a lot of times we build discovery machines, we launch discovery missions, we're trying to find something new. But when you're talking about theory calculations on computers, I feel like there's a different mindset. The sociology is different of making large investments for potentially no return.
no, that's a very good point. Before sorry, I did want to encourage, there is a question and answer period. I wanted to leave 10 minutes at the very end for questions. So I wanted to encourage attendees to post your questions in the question and answer section. But in terms of prepared questions, I did want to sort of turn this towards future generations, since part of the idea behind the Winter School is to provide a forum for students at both the graduate and undergraduate level to learn a little bit about applications of machine learning. I'm going to ask your opinion about what would be most useful uh, to learn. Is it algorithms? Is it base sort of discipline level knowledge, where is the mix between, studying more physics, for example, and studying computer science or machine learning algorithms? Uh, in your mind, where's the ideal mix? So I'm going to start with Jamie, and I apologize, I'm putting you on the spot in the sense that it's been a while since you've studied physics, but you did once, so maybe you can take your first stab at this.
Yeah, I did once. I mean, the the thing I think one thing I wanted to say very much related to this, so I've become I don't know whether I should call myself a former physicist or both a physicist and a computer science or scientist and someone who's getting back into trying to combine those things together. Um, uh, Patrick Winston, who ran the MIT AI lab for 25 years or so, starting in the 70s until the 90s or so. When I first met him and I told him I was a former physicist, he said, I like physicists, or I like working with physicists because they know how to model things. And I think that's something that's important. What's important to me, I think, in terms of the future, is both we want to learn more things about, we want to build AI systems and machine learning systems and learn more physics. I think, maybe slightly off topic, but interesting for the future is learning more, using our AI systems to learn more about human intelligence and learn more about the human mind, learn more about the mind of the physicist and the mind of the mathematician and of the scientists. Through those things and what motivates us. We aren't yet at the point where we can take a robot or an AI system and kind of aim it at the sky and say, discover some interesting physics there. What motivates us to want to learn these things and discover these things? Those are things that are very interesting to me for the future. But I think generally, the more that, and I think I mentioned this earlier, the more we learn about the human mind and how it works and the representations that we have, the better the combinations of, the better the human in the loop and the combinations between humans and our computing systems or AI ML systems can be, because those systems will know more about us.
Yeah, I agree. I mean, it helps with this issue of context and how a physicist views the world, to have some sense of where the differences are and actually how is it that we look at the world. Phiala, do you want to take a stab at this question?
Yeah. So, I don't think learning any of the specifics is to me what's important. I don't think learning some particular machine learning algorithm or even learning some particular key piece of physics is somehow the important thing. It's learning those things and looking into the guts and really understanding them. So if learning a machine learning algorithm, why is it that it's effective? What's it doing under the hood? Code it from scratch. And see, what is it about it that makes this efficient, so that you know how to then design a new one that's better, right? And with the physics, yeah, learn the physics that interests you, but that can change over time. Over your career, what interests you evolves, and so it's not collecting pieces of information. It's collecting the understanding of how to put them together, right? And so I think going into it with that mindset is, to me, the most important thing.
Brenda, can I put you on the spot for the same question?
Sure. So I think this combines what Phiala and Jamie were saying. So I think the most important thing to develop as a scientist is intuition. So that might be physical intuition, it could be chemical, it could be biological, it could be some of all of those all together. But that's really the key denominator. I think that's what makes us. I'd like to think what makes me or you, different than a computer right now, as we've been discussing. And that physical intuition, how you develop it, going back to what Jamie said, I'm not sure how I came to the point where I can sort of see where this problem might go or might not go. And, that's mostly what I do as a professor. Somebody gives me a problem and says, what's probably going to happen here. I don't know how that happened. but it's incredibly important. What I can say, what are the ingredients? A lot of it is exposure. You're here at this winter school. It's hearing people talk about the topics, reading about the topics, as Phiala was saying, getting into the guts of some things, that really helps. But being able to put all these threads together in order to, actually develop that representation in your mind such that you can sort through different problems quickly, that's incredibly valuable.
Yeah, and then one of the things, since I'm also serve as a concentration advisor, many of my advisees say, well, which classes should I take? Should I take the classes really quickly? And one of the things that we highlight about the way physics education works is you see everything multiple times, right? There's a joke that you see the harmonic oscillator in every single class. And part of that is because physics problems are reducible to similar equations, but also some of it is that intuition is built up over time, and that you shouldn't expect the solutions to happen all the time. That intuition happens. I mean, again, this may be self-serving as I am now many decades in, but it evolves over time, and you get deeper of that appreciation, and that's something that you don't necessarily get directly from a single class. It's that exposure aspect. Michael, can I close with you on what do you think a future student should be thinking about? And then there are a couple questions we'll try to address them.
Yeah, no, I really like this question. I don't think it has a good answer, though. Of course, everybody's answers were very good. But because in particular, it strikes me as reminiscent of the question of like, well, do we think theory or experiments are more important? Like, what should the right blend between theory and experiments should be? And I think the answer that we come to as a community is we want people that sit at different places in that spectrum. Somebody who's purely theoretical, somebody who's purely experimental, somebody who's got a little bit of a mix, a different mix. Like all those different mixes all seem to contribute because we don't know where the big deep insights are really going to come from. And so people who internally have kind of combined all those different ideas together are really well positioned to make breakthroughs. And I think the same thing is true on this kind of machine learning, actual physics spectrum. Is that it makes sense for the community to include some people who are just purely physicists and aren't thinking about the computational aspects at all. And there are people and it absolutely needs to be the case that we have people who are really deep into the physics, but also have some knowledge of how this might be implemented with the kind of systems that we have today. And all the way to, well, I'm mainly a machine learning person, but I'm going to use physics data. Like all those different data points, all those different spots along the trajectory are all adding value. And so that would be my answer, is to not give you an answer. Like we should definitely expose students to all those things, but I don't think we should set a slider and say, okay, everybody needs to be 18% computer science and 82% physics, because we don't know. We just don't know.
Excellent. I will also close by pointing out that collaborations are great, right? Physics is not done in a single person, and so having people with different levels of the different applications or different skills is what makes progress in our field, right? They're rarely, you're rarely the single person in a room with either a computer or a piece of paper. I do want to take, since we have about 10 minutes left, take a couple minutes to address the questions. So thank you for the three of you who submitted questions. The questions pick up some of these same themes. So the first question is, are there more potential applications in conducting particle physics experiments other than data analysis and reconstruction? And Phiala, you mentioned one of them. Do you want to elaborate on the theoretical modeling aspects of particle physics?
Sure. I mean, I can talk in a limited capacity about particle physics experiments, but I can talk about particle physics theory at great length. So you can use machine learning to accelerate calculations. Something I work on is calculations from first principles of the structure of matter. So how can we go from our understanding of the equations of the standard model of particle physics and go and calculate everything from proton structure up to nuclear physics, nuclear reactions directly. And so you can use machine learning to accelerate that. There's no data involved. There's no data analysis. It's trying to solve equations numerically that we couldn't solve any other way.
I would imagine also that there's a use for machine learning algorithms even in the design of experiments.
Oh, certainly.
That's a tricky business, right? Because of course you want to design an experiment to answer a question that you you're trying to answer. But certainly, as the new generation of accelerators is coming online, I'm sure the design will be, I know there are people working, for example, on, reducing the synchrotron emission from, lepton accelerators. And that's a case where designing this is a very complicated thing where machine learning can actually minimize, the physics, you can put the physics in, and whereas the solution is very complicated and expensive numerically, finding the right mix may well be a learning tractable problem. Um, it, on the issue of resources, there's a question on whether we think that energy and power constraints will ultimately limit what types of physics problems that can be realistically applied, one can realistically apply machine learning to. Someone want to tackle that? I know, Phiala, you'd mentioned this.
I can give a yes. I mean, energy and power constraints and available computing already limit with conventional algorithms what physics problems we can solve using conventional algorithms, and they certainly will continue to do so with machine learning.
Yeah, I'll just jump in. I continually, I guess I run some of the biggest calculations, and I guess I don't know, I always get the prize for running like the biggest DOE calculation, blah blah blah, every year, and that's using traditional physics algorithms. So in our case, we're interested in solving the Schrodinger equation, and so doing that and the way we've done it historically is incredibly expensive for large systems, and in that situation, it's an exponentially scaling problem. And so that has long limited things. And actually, ML is in principle going to be much faster as long as we have the data. So actually, from my perspective, what's actually going to be limiting for many of our problems is the data generation, both experimentally, which Jan was saying, it takes a lot of energy to get data. It also takes a lot of energy to run physics-based models, even more than the ML. And maybe I'm being a little bit naive about how big, the models could be, but if you don't have that data in the first place, which is expensive to get, it may be hard to imagine how you would scale there. So anyway, we've hit this problem in the past, and I think that will continue into the future.
Jamie, do you want to take your perspective?
Yeah, so this gives me a chance to plug a collaboration that I've been working on with Jan. So there are these problems with weak gravitational lensing that we've been working on, and we found a situation in which it seems likely that the conventional machine learning methods could help us if we had a few orders of magnitude more storage and compute power and data and so on. But we don't have that. And so we've been exploring, you could say, traditional symbolic rules-based AI systems in combination with these models from about 20 years ago, a lost thread called shapelets, to hopefully achieve some better solutions on the problem within the resources that we have.
Yeah, it's one of those things where everything is limited, right? You can't build there's not going to be a 100-meter telescope anytime soon. You can't collect more data. In my particular case, we have an extra problem that there's only one observable universe, right? So you can't actually replicate the observable universe. But there are ways.
It's just not a constraint that people often mention. So I think I really like that.
Yeah, cosmic variance is a real thing, right? So, but there are ways in which the resources that we have can be reallocated, and so where I think, as Brenda pointed out, there are places where machine learning can make things more efficient. There are places where it's not clear, as Phiala pointed out, whether machine learning is actually more of a resource. And so actually this leads into the third question, which is I'm going to selfishly take because it's about astrophysics, which is how is AI best able to assist research in astrophysics? And again, part of it is going back to the original aspect, which is the number of things that you observe, the number of pixels is more than you can ever look at in conventional algorithms. Right now, the Rubin Observatory is in commissioning. That commissioning, the data pre-processing budget for it is 3. In other words, the entire data set can only be reprocessed 3 times with the computing resources that are expected. So it means you have to be very parsimonious with what you do with the data. But there are ways of picking up subsets of the data and figuring out what you do with that data, and how do you analyze that data. So a lot of the actual advances that are coming online are not in the, I mean, there's still things going on in the sorting rare events aspect and discovery space, but a lot of it is in the how do you best take care of the information you have so that you can extract the things that you want. For example, how do you predict what the atmosphere is doing to the images? Because of course we're taking data from underneath a soup that's constantly moving. How do you account for that in the data that exists? Can you train your model to on a subset of the images to figure out how to improve all of them so you don't have to reprocess everything all the time? And I think that's one of those areas that we're going to be going to. Michael.
Yeah, I think that was awesome. I wanted to just flag so coming into my current role at Brown, I spent 3 years at the National Science Foundation, and right as I was leaving, a report got released specifically about the use of AI to solve problems in, well, the directorate is called MPS, Mathematical and Physical Sciences, but it includes physics, it includes astronomy, it includes astrophysics, it includes mathematics. And one of the things they pointed out specifically on this kind of astronomy space is the notion of the importance of uncertainty quantification, especially in that field where the data comes in and you're trying to do the best you can with it, but you're really limited in terms of the resolution that you have and the reliability of the signal that comes in, and so you have to be able to reason about that kind of uncertainty. And so yeah, I wanted to flag that report because if people want to kind of dig in and see what a community of scholars around this field had to say about the role of AI, it's really well done. They did a fantastic job.
So very rapidly, we have two quick questions. I think I'll tackle the last one last. The first one has a more technical long answer, but very quickly, the questions is are there issues? So given that a lot of the machine learning problems basically solve uh, partial differential equations, uh, have is there a bottleneck based on that performance? And Michael, I saw that you flagged yourself as looking at this question. Do you want to try to take a first stab at whether solving PDEs, which is after all what a lot of physics equations are about, going to be a bottleneck for AI?
Oh, I didn't mean to flag myself. How did I
Ah,
flag myself?
somehow you flagged yourself as answering this question live.
Oh, just that. Sorry, I was just. This is
You clicked on
the
it.
panel is answering it live. Sorry.
Yeah, so the question is in terms of convergence of PDEs. So PDEs are something that is done very much in the old style computational aspects, right? So that's often what a lot of what Brenda is solving are. Uh, is there an issue with MI not being able to solve those equations directly and trying to treat a different way? Is that going to become a bottleneck? So Brenda, Phiala, either of you want to take a quick stab at that?
Sure. I have a somewhat strong opinion on this. So many of you may know that for example, Brown is actually a leader in physically informed neural networks. So, for example, George Karniadakis runs the Crunch group here at Brown. He's famous for solving PDEs using ML. One thing I have to say about that, so there are definitely mechanisms. I think with more data, with more thought, we'll get there. What I do have to say is for many PDEs that physicists care about, and also I'll say engineers, people interested in fluid dynamics as well, talking about quantum mechanics and really fluid dynamics, the accuracy that you need is still too high. The resolution that you need is very, very small. So, when I'm things, I need resolution on the scale of many hundredths of an EV. And right now, ML is not there yet. And so, actually for us, like we're sort of like, that's great, you can do it using ML, but you're giving me answers on the scale of, I don't know, 10 EV. Not there yet. And so we have to think about how do we get there? There are tools that are being made, but we're not quite there yet.
Excellent. And I think the last question is, will AI ever be able to simulate physical lab experiments in the absence of actual physical apparatus? And I think this question goes to what Jamie started at the beginning, which is this issue of so the worldview of an AI, that AI isn't in the world. And so uh, if there is no data existing, it's hard to see how AI would actually be able to conjure up new data. As an experimentalist, this makes you feel happy, right? I'm not about to become unemployed in the next few years, but it is an important question of how much can AI pick up a real world view and pick up, what an experiment might actually build, as opposed to assist with an experiment. Michael, do you want to close us out with that?
Well, it feels like it relates really closely to the previous question, right? Because how would you simulate a big physical experiment? You'd probably set it up as a bunch of PDEs, right? And so the fact of the matter is we don't have, as Brenda's pointing out, right? We don't have a great way to just magically solve any old PDE, especially PDEs representing really interesting boundary cases that is what you're going to be setting up an experiment on. So I don't think I don't know. People in my field talk about, oh, we're just going to make world models. We're going to have these giant neural nets, and they're going to be world models. And I just like, no, that's not what machine learning is good at. It's good at the average case, the typical case. And I think experiments are really about finding the edges and revealing new knowledge.
On that note, I think since we've hit 2 o'clock, I would like to thank all our panelists. So thanks to Phiala Shanahan, to Michael Littman, to Jamie Macbeth, and Brenda Rubenstein. And I would encourage those of you who are attending the winter school. Our first introductory module is actually coming up in a half hour. In this Zoom session, we'll close this session and restart it. And so there'll be at 2:30, Sean Dubé will be going through an introductory module, which is intended to introduce concepts in machine learning, but also introduce you to the structure of the data formats that we'll be using for the other modules in the next few days. So I encourage you all to attend that. And with that, I would thank everyone involved and see some of you at 2:30. Thanks, everyone.
Thank you very much.
Everyone.
Thank you.